Hello everyone, my name is Zheng Zhang. Today I will talk about deep diving into documentation to develop improved Java to Swift API mapping. Its outline, let's begin with the introduction. Projects need to migrate different platforms and different programming languages. With the growing number of software, migration tools occur so as to reduce the cost of manual code migration, but they all face the challenge of API mapping. Next, we use an example to illustrate the API mapping. The following code fragments are testing whether the substring in string beginning at specified index starts with prefix. For Java, it needs one API starts with. For Swift, it needs two APIs. We first get a suffix, and then we use the starts API to implement the same function as Java. There are three types of relative work. The first is to collect bilingual projects and parse code. The second uses a statistic method based on API documentation. The third uses neural network. From the chart, we can see that the latter work focuses improving the performance of one-to-one API mapping. There are two metrics, PRF and top K accuracy, to evaluate the performance of API mapping. But they all face some challenges. First, the data is hard to collect. There is a limited number of bilingual projects, and there is only some Java to C# API mapping pairs. Second, most works generate cause API mapping. For example, they cannot handle parameter mapping, and many-to-many API mapping contains one-to-one API mapping. Third, most works statically parse code to obtain complete API information, but it's not applicable for dynamic programming languages, such as Swift. In order to alleviate these challenges, we study many API documentations and find they provide abundant API information, such as parameter and return description, that are ignored by previous works. Therefore, we hypothesize that we can use the information to improve the performance of API mapping. It's the approach. First is approach overview. We use API documentation as input and output ranked API mappings. The process contains two phases. The first phase is to extract API information model for each API. The second phase is to calculate the similarity of APIs and then handle one-to-many API mapping. Our approach contains three key points. First, how do we extract the information model for each API? Second, how do we compute the similarity between APIs? Third, how do we handle one-to-many API mapping? Next, we use an example to illustrate the specific process. The Java API documentation provides API signature, method parameter, and return description. In first step, we extract three-dimensional API information model that comprise behavior, input, and output information. The input and output information contains type and semantic information. In second step, we use vectorization and distance measure to calculate the similarity of APIs. In third step, we first build the API sequence graph and then design a dynamic searching algorithm to implement one-to-many API mapping. Next is the detail of our approach. First is preprocessor. We first standardize the API information, and then we simplify API documentation. The API information model is a five-tuple. The BEH represents functional description, consisting of several keywords. The PT is the parameter type set. The PS, it represents parameter semantic information. It's a dependency relation set. RT is the return value data type set. S is the return semantic information set. For behavior information extraction, we find that the API method name provides concise behavior information. Therefore, we can extract all method names as a keyword back S and extract the method name and the first sentence of a method description as keyword backs W1 and W2. Finally, we intersect W1 and W2 with S to obtain behavior information. For input information extraction, for parameter type information, PT, we extract data type based on parameter list of the API signature and parameter description. For parameter semantic information, we find that the API documentation also writes parameter description based on parameter name in API signature. Therefore, for each parameter, we can extract a two tuple. The one is the parameter name, the other that has a dependency relation with the parameter in parameter description and method description. The output information extraction is similar to the input information extraction. Next is the similarity computation. We first vectorize API information. For semantic information, we use word-to-vector that is widely used in word embeddings. For class type, we cannot use word-to-vector because class name doesn't frequently occur in API documentation. But for each class, it contains all API's information. Therefore, we can use statistics method to vectorize class type. For behavior information similarity, we first average all vectors of behavior information of one API, and then we use cosine to calculate the similarity of two averaged embeddings. For input information similarity, we first use cosine to calculate the parameter type similarity matrix AT and parameter semantic similarity matrix AS. And then we use the Hungarian algorithm to maximize the similarity to implement parameter mapping. Finally, we merge the type similarity and the semantic similarity to generate input information similarity. The process of output information similarity is similar to the process of input information similarity. Finally, we use a weighted summation to obtain total information similarity. Finally, it's the API sequence generation. We first build an API sequence graph based on data type dependency. And then we traverse the API sequence graph to handle one-to-many API mapping. For a given source API, we first add one target API and calculate the parameter similarity P1. And then we traverse API sequence graph and add one target API and calculate the new parameter similarity P2. If the increment of a parameter similarity is larger than the given threshold and the parameter mapping is valid, we repeat the process. Otherwise, we use the old API sequence as a valid target API sequence. Next is the evaluation. We research three problems. First, what's the effectiveness of our approach? Second, is it necessary to use three-dimensional information? Third, what is the effectiveness of our approach compared to current works? It's the experiment setup. We apply our approach to Java to Swift API mapping. We crawl Java and Swift API documentation. In order to select Java server jets, we crawl 20 Java projects from GitHub and call the API use frequency. And then we orderly select 15 different Java classes in order to make a convincing API mapping datasets. 3 programs separately make the data, and we distribute the data to 65 graduate students to verify the data. Finally, we make 259 one-to-one API mappings and 28 one-to-many API mappings. Next, we calculate the top K accuracy of one-to-one API mapping. The top 10 accuracy is 0.76. Therefore, our approach can effectively handle one-to-one API mapping. And then we analyze the reason of failing to find correct API mappings. The blue means that the behavior similarity of correct API mapping is lower than of wrong API mappings. It occurs for more than 50% because the word word cannot recognize synonyms and antonyms. The red means the input information similarity of correct API mappings is lower than of wrong API mappings because the gap of input in semantic information and the input data type between two APIs. The green is the integrated reason of behavior and input similarity. The purple means that our approach wrongly finds the one-to-many API mapping for the one-to-one API mapping. Next is the one-to-many API mapping. The top 10 accuracy of one-to-many API mapping is 50%. The EDR editing distance is about 0.2, which means that our approach can effectively modify raw API mappings. Next is the parameter mapping. The percent of no parameter mapping error is more than 80%, which means that our approach can effectively handle parameter mapping. Next is the characteristic of API mapping. The percent of successfully finding different characteristics of API mapping is 71%, which means that our approach can effectively handle diverse API mappings. Finally, it's the characteristic of one-to-many API mapping. For example, the large difference of class names between the source API and the target API. The parameter of the source API can exist one-to-many API mapping, and the target API sequence can involve many classes. The one-to-many API mapping makes a considerable portion of mappings. A total of 40 API mappings were found. In order to answer the second problem of the effectiveness of three-dimensional information, we trace the weights of behavior input-output information. We compare top 10 accuracy of three-dimensional information with one-dimensional information and two-dimensional information. From the two charts, we can see the top 10 accuracy declines. Therefore, the three-dimensional information is beneficial for API mapping. Finally, we compare with current works. We first compare with documentation-based DMAP. From the table, we can see our approach is superior to DMAP. Finally, we compare with code-based approaches. For top 10 accuracy, we compare with SAR. Our approach is slightly superior to SAR in top 10 accuracy, and our approach can handle one-to-many API mapping, but SAR cannot handle it. For PRF, we compare with StarMiner and DeepAI. For StarMiner, we use 11 bilingual projects, but it can only find one-to-one API mapping. For DeepAI, we find that the small size cannot get the same good reported result when applying to JavaScript API mapping. In the end, we give the conclusion. We propose to build the three-dimensional information model by thoroughly examining API documentation. Second, we propose an approach that can handle one-to-one and one-to-many API mapping with parameter mapping. We evaluate our approach on 259 one-to-one and 28 one-to-many API mappings. The results show that our approach performs better than existing approaches. Thanks and welcome any questions.